Hi everyone, it's Mrs. Martello. We're going to look at section 3.2. So in this section we're identifying whether a function is linear or non-linear. So those are our two options. It could be linear or it could be a non-linear function. So what I did was I put the information into this visual representation here as a chart, and I think that this is a really nice thing to copy down. So I would highly suggest you pause the video and copy this down into your notes. So this is how we're going to identify a linear function given to us in various forms. First, it could be given to us in a graphical form. So as a graph, what we're really looking to see is that the graph forms a line. So if it forms a line, then it would be a linear function. Just as a side note, it cannot be a vertical line. A vertical line technically does not pass the vertical line test, which we learned in section 3.1. And because it doesn't pass the vertical line test, it's not even a function. So if it's not a function, then it cannot be a linear function. Okay, so it can be any line, but just not a vertical line. Okay, the next thing that we can look at is a table. So in a table of values, you want to look for the pattern of what's happening with the x's and what's happening with the y's. You want to see that the x's are adding by a constant amount and that the y's are also adding by a constant amount. They can be different amounts for the x's and the y's, but they have to be constant within the same variable. So this is a table that is an example of a linear function because the x's and the y's have a constant rate of change. And again, we're adding by the same number. Okay, our last option is an equation. And I gave us two examples here for this one. The equation y equals 2x plus 1, that would be a linear equation. And also 3x plus 4y equals 12 would be another linear equation. So what we're looking for is that the equation can be written in the form y equals mx plus b. This form, y equals mx plus b, we're going to become very familiar with this form. Just to introduce you to what it's called, this is called Slope-Intercept Form. And we're going to do more with this form later in this chapter. So if you have never heard of Slope-Intercept Form yet, that's okay, but we will learn more about it. So I'm just going to talk about this equation. The first one, it definitely does look like y equals mx plus b. We have y equals 2x plus 1. So the 2 stands for the m and the 1 stands for the b. So that is definitely in the right form. In the second equation, it's not in the correct form right now. However, if I asked you to, you could solve this equation for y, like how we did in section 1.5. If I asked you to solve for y, then the equation would be in the correct form, making it a linear equation. All right, so these are the three things we want to focus on, is the graph, the table, and the equation. Let's look at some examples. We're going to look at example 1. So does the graph represent a linear or nonlinear function, and explain? So here in example 1a, this graph is a curve. It is not a line. So because this graph is not a line, it is nonlinear. In example b, this graph is a line, so it is linear. The graphs are pretty straightforward. Let's take a look at example 2. We're going to look at the table. So in example 2, again, we want to look at the pattern for the x's and the y's. So in part A, our x's go plus 3, plus 3, plus 3. That's good. Let's look at our y's. Our y's go minus 6, or you can say plus negative 6, and then minus 6, or plus negative 6. So technically the x's add by a constant amount, and the y's add by a constant amount, or subtract. So that means yes, this graph does represent a linear function because it has a constant rate of change. Let's take a look at letter B. So in our x's go plus 2, plus 2, plus 2. So our x's are good. But our y's, to get from 2 to 9, that's plus 7. To get from 9 to 20, that's plus 11. To get from 20 to 35, that's plus 15. So because these changes in y's are different, that means it is not linear, because the rate of change is not constant. So this is a non-linear function. Okay, let's take a look at our next example, which is example 3. We're going to look at the equations. So in the equations, we want to identify each of the equations here. So our first equation, y equals 3.8. Yes, this equation would be a linear equation. Let's read what it says down here. Technically, we can write it as y equals 0x plus 3.8. So technically, it can be written in that form of y equals mx plus b. So it is a linear equation. The second equation, y equals the square root of x. No, that is nonlinear. We don't want to have square roots. That would be a square root function. That's nonlinear. Let's look at this equation, y equals 3 to the power of x. No, that is not linear. We do not want x as an exponent. We want x to be multiplied by the 3, not raised to the power of x. This would be an exponential function, so it is non-linear. Our next equation, y equals 2 over x. No, this is non-linear. We cannot have this variable in the denominator that makes a rational function, which is not a linear function. So we want x to be in the numerator. This is non-linear. Let's take a look at this equation, y equals 6 times the quantity of x minus 1. Yes, this equation can be simplified. If I were to distribute this x to both of these terms, then I'm going to go down here. I can simplify the equation to be y equals 6x minus 6, and that is in the form of y equals mx plus b, so this is a linear equation. So it doesn't say plus here, but remember minus is the same thing as plus negative 6. So this is in that form, y equals mx plus b, and it would be linear. Let's look at our last equation, x squared minus y equals 0. This is no, because we cannot have x squared. X to the second power is a different kind of function. It is non-linear. We need x to be to the first power. So this is no, this is non-linear. Okay, down here at the bottom of this page, they have a nice concept visual representation here of what we just kind of talked about, but this is very similar to the chart that we started with on the beginning of our notes page. Let's take a look at some more examples here. We're going to go over to the next page. All right, when we are graphing our linear functions, we're going to start off slow with our graphing, and we're going to make a t-table to graph these functions. So in order to do that, we want to look for the solutions of a linear equation in two variables are going to be an ordered pair x and y that make the equation true. So the graph of the linear equation is all the set of all of the points in the coordinate plane that represent all the solutions of the equations. Okay, so you make a t-table, you pick different x's, you plug them into the equation, you find the y's, and then you plot them. Sometimes the points are distinct, and other times the points are connected, and those are called two different things. So I'm going to write this down so that we have them. A discrete domain is the set of input values that consist of only certain numbers in an interval. So it's these individual x's, whereas nothing is in between. Remember, domain is the set of all the x's, or the input values. So I'm going to write that down here. It's when the inputs are individual numbers. Sorry, I spelled that wrong. Individual numbers. In other words, they are separate. They're not together. They're not connected. Okay, so a thing that we want to think about for this is we want to think about when the domain or the x's can be integers. So basically no decimals and no fractions that we're thinking about here, okay? The other kind of domain that we're looking at is called a continuous domain. A continuous domain is when all of the x's are connected. and it's every single number included in between that interval. So it's all numbers in the interval. Okay, so it's the inputs are all the numbers in the interval. Okay, so for example, for this is when we have their x's can be real numbers. And remember, that includes decimals and fractions as well. So that's really an idea you want to think about. Okay, that's the biggest difference. These are individual points, which means they're all integers, and these are all connected in between because you can include all the decimals and fractions. Okay, let's take a look at an example like this. This is example number 4. So the linear equation y equals 15.95x represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function, and is it discrete or continuous, and explain. So our domain are the x's. The x's are the input values. Those are our tickets. So think about how many tickets you can buy. You can buy 0 tickets, 1 ticket, 2 ticket. Notice how I'm stating integers here. You cannot buy 1.5 tickets. So because this is integers, that means that this must be a discrete domain because it's only those specific values. So here, because you cannot buy a part of a ticket, only certain numbers of a ticket, because x represents number of tickets, it must be a whole number, and the maximum amount of tickets you can buy is 4. So the domain here is going to be 0, 1, 2, 3, and 4, and it is discrete. Okay, so remember up here it says the maximum was 4 tickets. So you can buy 0, 1, 2, 3, or 4 tickets. Okay, our next step for part B is we're going to graph the function using the domain. And notice how they made this nice t-table here. This t-table is a nice way to do this. So we're going to have our input values of 0 through 4. Then we're going to take each of these x's and plug them into our equation, find out what they equal. So 15.95 times 0 is 0. 15.95 times 1 is 15.95. And then times 2, times 3, times 4, and we get these values here. Now the inputs and the outputs create an ordered pair, 0, 0. This input and output makes an ordered pair, 1, 15.95. And then you keep going and you list all your ordered pairs. Then finally, you can graph the points. So this is a nice coordinate plane that they have here. So if you're using a coordinate plane, then you plot them as best that you can and make your axes and label them, decide what you're gonna go by on the axes. Your x's here, they went by 1s, and the y's here, they went by 10s, which makes sense. And then you just plot your individual points and you keep them separate. You do not connect them because remember, it's nothing in between these values. It's only these values. Okay, I'm gonna post a link in Classroom for you to print out some coordinate plane paper. That's free. If you'd like to print out coordinate plane paper, it's easier to make graphs on there. But if you don't have a printer, then you can just do your best on your notebook paper. Okay, let's take a look at monitoring progress number 8. Okay, we're gonna do this question together just to make sure that we know what's going on. So in number 8 here, it says the linear function m equals 50 minus 9d represents the amount m in dollars of money you have after buying d DVDs. Find the domain of the function. Is the domain discrete or continuous, and explain, and then graph the function using its domain. Okay, so let's think about what our domain is here. The domain is the x's. In this case, it's what is the independent variable. Remember that the domain represents the independent variable. And remember, that's the variable that we have control over in this case. We control how many DVDs we're gonna buy. And look at how D is the input value in this equation and the output value is the M. So that's going to be D, and that's the number of DVDs. Okay, so that is what our domain is going to represent. Okay, let's think about how we're going to state our domain. Well, how many DVDs can we buy? Well, we can start with 0 DVDs. Let's keep thinking about how many can we buy. So if I have 0, I would plug 0 in, and that means that I would have $50 remaining. If I plug in 1, then that would mean 50 minus 9 would give me $41 remaining. So maybe it might be easier to make a table here. It might help us kind of figure out what we have going on. So let's set up a table, and I'm going to go horizontally here for our x's, then I'll have the equation, and then I'll have our y's, or actually I should say M, and I should say D for DVDs. All right, so our first DVD value is 0. If I plug in 0, 50 minus 9 times 0, that would be $50 remaining. Let's plug in 1. 50 minus 9 times 1, that would be $41 remaining. Let's keep going. We're going to plug in 2. 50 minus 9 times 2, 50 minus 18, that would be $32 remaining. Do you notice that there's a pattern that's happening with the y's? Do you see how the x's were going +1 each time? Look at the y's. Do you see how the y's are minus 9 each time? Well, this is a linear function, so that's what exactly should be happening here. So I'm going to keep going. We're going to have 3. Let's keep going with this. Minus 9 is going to give me 23. Okay, if you want to plug it in, you can plug it in, but that's going to end up what you get because we're just going to continue the pattern, keep minusing 9. Then if we have 4, let's minus 9, we'll have $14 remaining. 5, let's minus 9 again. And we'll have $5 remaining. So think about what this means. Can I buy another DVD? If I buy a 6th DVD and I subtract $9, that would leave me with -$4, but you can't have -$4. That does not make sense. So we can only get up to 5 DVDs. So our domain is going to be 0, 1, 2, 3, 4, and 5. Okay, so that's our domain for this one. And now think about what this means. If it's these individual numbers like this, that means that this is a discrete domain because it's those specific whole numbers. These are whole numbers. Okay, let's go on to part B. Part B, it says we want to graph the function using the domain. So we're going to take these x values and these y values and we're going to graph them. So if you have graph paper, you can grab your piece of graph paper. If not, that's okay. Now I'm only going to include the positive values in my graph because we can't have negative money and we can't have negative DVDs. That wouldn't make sense. So our DVDs go on the x-axis and our money remaining goes on the y-axis. Okay, and I'm going to set up my graph just like how they did in the book. So this would be 0, 1, 2, 3, 4, 5, 6, and this is the DVDs. And then for our money, I'm going to go by tens. 10, 20, 30, 40, 50, 60, 70, and this is money remaining. Okay, let's plot these points. I'm gonna start with the point 0, 50. Let's plot that point up here. Then 141. So I'm just gonna estimate, here's 1, and then it'll be a little tiny bit above 40. 232. So here's 2 and just a little bit above 30. 323. So here's 3 and a little bit above 20. Then our next point is 4 and 14. So almost halfway. And then finally 5 and 5 would be right about here. So that would be our graph for this function.